Welcome to lecture 64 on essentials of topology. In the previous lecture, we have studied the concept of regular spaces and also we have seen a number of examples. In this lecture, we will study some of the results on regular spaces. Further, we will also study the concept of normal spaces. Begin with, let us see a result on regular spaces. Precisely, this is a characterization of a T3 space. The result is stated as that a topological space X tau is T3 if and only if for each X in X and for each open set G containing X, there exists an open set H containing this X itself such that closure of H is a subset of G. In order to justify it, let us assume it and we have to prove this part. In order to prove it, let us assume an open set containing X. So what we are taking? We are taking a subset G of X. This is open and this is containing X. Note that the given space is T3. So if we want to use the power of a T3 space, we require a closed set. So why not let us take its complement AGF, because G is an open set. Obviously, F will be a closed set. Further, it is to be noted that X cannot be element of F. So we can use the definition of a T3 space. By using the definition of a T3 space, what we can conclude? We can conclude that there exist open sets. Let us take them H and H dash such that what we can conclude that X belongs to H. This F is contained in H dash. Also, H and H dash are disjoint. Now, let us use this statement, that is, if H and H dash are empty set, what we can conclude? We can conclude that H is subset of complement of H dash. Also, it is to be noted that because H dash is open, its complement is closed. And if this is closed, if we are taking closure, we can say that closure of H is subset of this H dash complement. Further, what F is? Note that F is contained in H dash. So, if F is a subset of H dash, we can say that this F complement is superset of H dash complement. But what F complement is? That is nothing but G. It means that H dash complement is contained in G, or what we can deduce from here, that closure of H is contained in G. That's the proof of this part. Let us see the proof of converse part. In order to prove the converse part, let us assume it, that is, for each X in X and for each open set G containing X, there exists an open set H containing X with the property that closure of H is a subset of G. Now we have to justify that this topological space is a T3 space. In order to justify that this topological space is a T3 space, begin with an element X in X and a subset F of X. It is to be noted that F is closed. Also, X is not an element of this F. If we are beginning with this one, why not let us take a set G which is complement of F, because we have to use this statement and this statement is based on the concept of open sets. So if we are taking G as complement of F, what we can say that this G is an open set. Further, X is an element of G. Now we can use the assumption, and as per our assumption there exists an open set. Let us take that open set as H. And what is the property of this H? That this H contains X such that closure of H is a subset of G. Now if closure of H is a subset of G, what we can say that if we are taking the complement of this closure, this will always be superset of G complement. But note that what G complement is, that is nothing but F. That is, F is contained in this H bar complement. Also, it is to be noted that X belongs to H. Thus, we have got an open set H which is containing X. And also, let us take this H bar complement as H dash. So, we can say that this F is a subset of H dash. And what this H dash is? This is also an open subset of X because H closure is a closed set and its complement is an open set. Further, what we can conclude? We can conclude that H intersection H dash will always be an empty set, and this is followed from the fact that H dash is nothing but closure of or complement of closure of H. Thus, for a closed set and an element which is not in this closed set F, we found two open sets H and H dash. They are disjoint, and H is containing X while H dash is containing the closed set. Therefore, this topological space is a T3 space. Moving ahead, what we have already seen that a Hausdorff topological space may not be a regular space, but what can be justify that if with Hausdorffness, if we are adding the notion of compactness, then a compact Hausdorff topological space is regular. In order to justify it, let us take a topological space X tau. This space is compact plus this is Hausdorff. Now, if we are taking a closed subset of this X, let us take that this is closed, and let us take an element of X while this X is not element of F. It is to be noted that because this space is compact, what we can say that this F will also be a compact subset of X. In the previous lecture, we have already studied that if the topological space is Hausdorff and we have a compact subset of F which is not containing X, so by using that result, there exist open sets G and H. One is containing the point, one is containing the compact subset, and G intersection H is an empty set. So from there we have shown that this topological space X tau is a regular space. Moving ahead, and let us see some of the results. These results we are not proving here as these are similar what we have seen in the case of Hausdorff topological spaces. The first result is that a subspace of a regular space is regular. The second one is that regularity is a topological property, and finally product of regular spaces is also regular. So just think on proof of these results. I am leaving these as such results we have already seen in case of Hausdorff topological spaces. Moving ahead, so till now what we have studied, we have seen that if we are having a topological space X tau and if we are having an element as well as a closed set which is not containing the element, we can construct two open sets. One is containing the point and one is containing the closed set. Now we are moving one step ahead, and what we want to see that whether B can separate two closed sets. Meaning is to say that if we are having a topological space, let us take two closed sets in this space, that is, these are some closed sets. Let us take these as A as well as B. Question is, can we construct two disjoint open sets? One is containing this A and one is containing this B. If this is possible, we say that x tau is T4. Also, if we are adding one more concept, that is concept of T1 spaces, such spaces are known as normal spaces. Formally, a normal space is defined as given here, but before defining a normal space, let us see the concept of a T4 space. What precisely it is? So we say that a topological space X tau is T4 if for each pair of disjoint closed subset A and B of X, there exist open subsets of X, let us take them as G and H, such that one open set is containing a closed set, that is A, another open set is containing another closed set, that is B, and these open sets should be disjoint too. Finally, we say that this topological space is normal if it is both T1 as well as T4. From the definition, this is clear that if a topological space is normal, then that space will always be regular. Question is how it is possible? Answer is, if we are taking a topological space X tau, let us take that this space is normal, then what does it mean? It means that this is T4 plus T1. Now if we are taking any closed subset f of x, this is closed, and let us take an element x of x which is not in f. It is to be noted that this singleton set X is closed. Why? Because the space is T1 space. So now we have two closed sets with us. Now let us use this definition of T4 space. So what we can conclude? We can conclude that there exist open subsets or open sets G and H. They are subsets of X such that this G is containing this singleton set X. This F is a subset of H. Finally, this G and H are disjoint too. Or from here, we can conclude that X belongs to G, F is a subset of H, and this G intersection H is an empty set. Thus, what we can say that this space X tau is a regular space. Now, question comes whether regular spaces are normal too. Answer is no. That is, if a space is regular, it doesn't mean that space will be normal. Even before discussing normality as well as regularity, it is important to see the relationship between T3 as well as T4 spaces. Similar to the relationship between T1 and T2 spaces, what we can justify that if a space is T3, it may not be T4. Even a space which is T4 is not necessarily T3. So, let us see some of the examples of normal spaces, and in between we will try to justify these statements. So, begin with the first example. We have already seen the concept of this topology, that is known as right ray topology on R. For this topology is, we have seen that if we have set of real numbers with us, right ray topology on R is given as collection of empty set, this set of real numbers along with the intervals of this form, that is a to infinity, where A is a real number. Now, question is, what about closed sets? So, try to find out two disjoint closed sets. Answer is here. If we are looking for non-empty disjoint closed sets, we cannot find in this case because how the closed sets will look like. For example, if this is any open set A to infinity, so what will happen? The closed set will be something like this one. So this is nothing but minus infinity to A. If we are taking another open set, that is B to infinity, so how the closed set will be? This will be minus infinity to B. Note that these two closed sets are not disjoint. So what we can say that this topological space, that is this set of real numbers along with this right ray topology, this is a T4 space. It is to be noted that this is not a T3 space. Question is why? Answer is, if we are taking this real line, let us take a closed set which will look like of this form, that is something like minus infinity to A. So we are taking this closed set in this topology. Let us take a real number B where A is less than B. So obviously this B cannot be an element of this closed set. But question is, can we find two disjoint open subsets of R? One is containing this closed set and another is containing this B. Answer is no, because the open set which is containing this closed set will also contain this element. Therefore, this is not a T3 space. Question is whether this space is normal. Just think on it. Moving ahead, let us take another example, and that is from metric spaces. So let us take a metric space xt and let us take this metric topology on X. So this is a metric space. What we can say that every metric space is a normal space. We have already discussed that this space is a T1 space. What we have to justify? We have to only justify that this is a T4 space. So let us try to justify that this metric space is T4. And in order to justify that this space is T4, let us take two subsets of X. These A and B are closed and they are disjoint too. Now, if they are disjoint, then we can conclude that this A intersection set of limit points of B will always be empty set, and also this A dash intersection B will always be an empty set because A and B both are closed subset of X, and if they are disjoint they will be separated too, that is A will not contain the limit points of B and also B will not contain the limit points of A. And if this is the case, what we can say that for all A in A, we can construct a member from basis for this metric topology. Let us take, that is, this is an open ball centered at A with radius, let us take this is RA intersection, this P will always be an empty set. And similarly for all B in B, what we can do that there exists some RB such that this A intersection, this open ball centered at B with radius this RB is always an empty set. This RB is a real number greater than 0 and also this RA is a real number greater than 0. Now From here, let us try to construct open subsets of X containing A as well as B. How we can do it? Answer is simple. Let us take union of these open balls, and why not let us take the center at A with radius that is half of RA. If we are taking this union, let us take this A belongs to A and we say that this is G. So what will happen? This is clear that G is open subset of X, even A is always subset of G. Further, if we are taking this union of open balls centered at P and radius RB by 2, where B belongs to this B. If we are taking this is H, note that this is also open and this B is a subset of this H. Finally, one thing need to justify that this G intersection H is always an empty set. In order to justify it, let us see what will happen if there exists some element in this intersection. So, if Z belongs to this G intersection H, what will happen? It means that this Z is an element of G and also this Z is an element of H. Now, if Z is an element of G, obviously that will be an element of sum of open balls. Similarly, this Z will also be member of sum of open balls of this form. So, what we can conclude that there exists some A in A and also some B in B, such that what we can say that this Z is a member of this open ball centered at A and radius that is RA by 2, as well as this Z is member of this open ball centered at B and radius RB by 2. And if these are the cases, what we can conclude that this DAZ is less than RA by 2. Also, what about this ZB? This is less than RB by 2. Now, if we are using triangle inequality, what we can conclude? If we are finding out this DAB, this is less than or equal to DAZ plus we can also write this is DZB, and this quantity will always be less than RA plus RB upon 2. Now, if we are talking about this maximum of RA and RB, so if for example this RA is maximum of these RA and RB, what we can conclude? We can conclude this DAB is always less than RA, and if DAB is less than RA, it means that B belongs to the open ball centered at A and radius RA. But at the same time, it is to be noted that B is a member of this closed set P. That is, this B intersection, this open ball centered at A and radius A is non-empty. And this is contradicting this fact. So, we reach to a contradiction. Similarly, in other case, if RB is maximum of this RA and RB, we can reach to a contradiction. Thus, in any case, G intersection H will always be an empty set, and hence we shown that there exist two open sets or two disjoint open sets. One is containing the closed set A and one is containing the closed set B, and therefore this space is a T4 space, and hence this is also normal. From here, it is clear that if we are talking about this real line with Euclidean topology, this space is also a normal space. Moving ahead, and let us take one more example, because we have shown that this R with standard topology is normal. What about this set of real numbers with lower limit topology? It is to be noted that this is also normal. And if this is normal, even we can show that this is regular too. How this is normal? Note that for normality we have to show that this is T1 plus T4, but this space is T1 because this is, or this topology is finer than the Euclidean topology, and we have already shown that R with Euclidean topology is a T1 space. So again we have to justify only that this topological space is a T4 space. Now in order to justify it, let us take two closed subsets of R and they are disjoint. What logic we have used in case of matriceable spaces? We can say that this A intersection B dash is always an empty set, and also A dash intersection B is always an empty set. So what we can do that we can find some basic open set here, that is for all A in A. What we can do that we can construct a basic open set. Let us take the semi-open interval closed at A, and this is A plus epsilon A. This intersection B will always be an empty set, and if this is true, we can find this semi-open interval B plus epsilon B. Intersection A is an empty set, and this is true for all B in B. Now let us take their union, that is if we are taking union of these intervals, let us take A plus epsilon A, where epsilon A and epsilon B both are real numbers and both are greater than 0. Now if this A belongs to A, this union, let us take that this is G, then this is trivially an open subset of R with respect to lower limit topology. Similarly, we are taking H as union of B belongs to B, this semi-open interval B and B plus epsilon B, then this is also open. Further, what we can say that this A is contained in G and this B is contained in H. Finally, the question comes whether this G and H are disjoint. Answer is yes, and we can show it. How to justify it? Let us see. For example, if possible, this G intersection H is non-empty. If this is non-empty, what will happen? There exist some semi-open intervals of this form as well as some semi-open intervals of this form, so that they have non-empty intersection, meaning is to say that there exists A in A and also there will exist B in B, so that we can conclude that this A plus epsilon A intersection this semi-open interval B plus epsilon B. This is non-empty. Now let us see these intervals on real line. So what we are taking that this is something like A to A plus epsilon A. Note that we are saying that they have non-empty intersection. So B will be something like here, and this is B plus epsilon B. What we have assumed here that A is less than B. Similarly, one can talk about when B is less than A. So what exactly the things will happen here, that is if we are taking this B as maximum of these A and B. If this is the case, so what will happen? This B will be member of this open interval. So let us take this is something like GA, and let us take this is something like HB. So this B belongs to GA as well as B belongs to HB. Now if B belongs to GA, what GA is? That is B is this interval, that is A plus epsilon A. At the same time, B is an element of B, but as per our construction, this B as well as this semi-open interval both are disjoint as stated here. So B reads to a contradiction. Similarly, if we are taking this A as maximum of A and B, what we can show that or B can reach to a contradiction. Just try to think on it. That is, in any case, if G intersection H is non-empty, B will reach to a contradiction. Hence, this space or hence G intersection H will always be an empty set, and thus this R with lower limit topology is a normal space. Also, this will always be a regular space. Question is, what about the product of these two spaces? So if we are taking the product, that is R2, and the topology on R is lower limit topology, so we are talking about this one. We have already seen that the product of regular spaces is a regular space, therefore this will always regular. But interestingly, this is not normal. Just think on it. This is not straightforward to justify that this R2, and when we are taking the product topology, it is to be given that R is endowed with lower limit topology, then this product space is not normal. And from here, one more thing is clear, that product of or product of normal spaces need not be normal. Moving ahead, similar to the concept of regular spaces, what we can justify that every compact Hausdorff space is normal. In order to justify it, let us take a topological space x tau. This is given that this is compact plus Hausdorff. What we have shown, we have already shown that this space is regular. Now, if we want to justify that this space is normal too, let us take two disjoint closed subsets of X so that these are closed, and also what we are taking that these two are disjoint. Now, let us use this regularity of the space. If we are taking any A in A, that is for all A in A, it is to be noted that A cannot be element of B as A and B are disjoint. So by regularity, there exist open sets. Let us take these open sets as GA and HA such that what we can conclude? We can conclude that A belongs to GA and this B is a subset of HA. Further, this GA intersection HA will always be an empty set. It is to be noted that such GA exists for each and every A in A. So why not let us take the collection of the GA where A is in A. Note that this will be an open cover of A. What A is? Note that A is a subset of X. This is closed. And what X we have taken, this is compact. So what we can conclude that this A is compact too. Thus, from here or by using the concept of compactness, from here we can construct an open subcover or subcover of this C, that is A is subset of GA1 union this GA2 union this GAK. Also note that corresponding to every GA there will be an HA, and GA intersection HA is an empty set. So why not let us take this is HA1, let us take HA2, and let us take HAK corresponding to each open subsets of this form. And if we are taking their intersection, it is to be noted that every HA is containing B. Therefore, their intersection, this will also contain B. Why not let us take this as G and this as H? So, what we can say that there exist two open sets, and these open sets are G and H respectively, such that what we can conclude that A is contained in G, B is contained in this H. Again, the big question is what about G intersection H? Note that this will always be an empty set, and such type of constructions we have also done earlier. So just think on it. Thus, what we have justified? We have justified that two disjoint closed subsets of X can be separated by using two disjoint open sets. Therefore, this space, that is this X tau, is T4. Further, being this is an Hausdorff space, this is T12, and therefore we can conclude that this space X tau is a normal topological space. These are the references. That's all from this lecture. Thank you.